Hello, welcome to today's colloquial talk. It will be given by Steve Butler. It will be on mathematics of juggling. It may include some theoretical as well as practical things.
All right. Well, I'm glad to give this talk here. I've given this talk at a lot of places, or at least I've given variations of this talk. This is sort of a combination of some talks that I've given. But I don't know if I really had a chance to give a nice talk about juggling here at Iowa State. So I hope I succeed this time. So I'm going to talk about math of juggling. Now, it's not so obvious that there's a lot to say about the math of juggling. It's certainly true that math and juggling have both existed for thousands of years. If you go back and look at the, for example, the records left behind by the ancient Egyptians, you can see there's the Orion Papyrus, which has one of the oldest homework assignments. And around the same time, you'll see that there's actually a picture on a tomb that looks like people are juggling. And so we know that they've existed for a long time, but math of juggling, that's a more recent sort of phenomenon. And I got really interested in this subject with working with Ron Graham. Now Ron is a very good mathematician and also a pretty good juggler. And we've been working together now for about 15 years. And at one point in his life, he was the president of the International Jugglers Union. And one of the things he said is that juggling is the art of controlling patterns, and mathematics is the study of patterns. So perhaps there is a nice connection. Now, as I said, Ron is a pretty good juggler, and if you were to start counting, you'd see that there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 balls there, which is really remarkable considering the world record is 11. So, on a side note, Ron's daughter, Cheryl, is one of the world's best Photoshop people. If a celebrity needs to look 20 pounds lighter, they call her. All right. So to start today, what I want to do is I want to sort of motivate and give a nice presentation of a result. It's a combinatorial result called Pixies identity. And we're going to give a bijective proof of Pixies identity, or some might call it a combinatorial proof. The interesting thing is that the only known combinatorial proofs are actually tied to juggling. And the first combinatorial proof was in a paper written by Ron Graham and Joe Butler. This is sort of a variation thereof. We're almost going to have almost the whole proof. There'll be a few things that I try to point out that I don't give you all the details, but if you want, I can follow up with you later. So before we get to the proof of Pixies identity, we have to say, what is Pixies identity? Which means we have to start with, what are Eulerian numbers? So Eulerian numbers are what are called a permutation statistic. So we're trying to count something with permutations. So one of the ways to think about a permutation is you can think about it as you have this nice board here. And a permutation says, look, I'm going to map the numbers 1 to n to the numbers 1 to n in a bijective way. So if we think of our inputs as 1 to n and our outputs as 1 to n, we can put a little marker, or if you like a rook, on each place where I get a map. Now, because I have to map everything, there's one rook in each row. Because I'm not allowed duplicates, there's one in each column. This is sometimes called a rook placement. So for every rook placement, there's a permutation and vice versa. Now, what the Eulerian numbers are counting is they're counting something called a drop. What's a drop? Well, it's when you map by the permutation and you end up smaller than what you map to. So for instance, if I put in 4 and out came 1, that's a drop. Now, if you think about it in terms of the picture, it's this part down here. This region here is where the drops are. So anything below the main diagonal. So this permutation has 3 drops. Now, once you know the statistic, it's not too hard to count these for small cases. And here on the screen, we have the Eulerian numbers for n equals 3. So there's one Eulerian number where there's no drop, there's 4 where there's 1 drop, and there's 1 where there's 2 drops. Now, other than the definition, there's one more fact we need to know, which is that there's symmetry. And you can see it, the 1, 4, 1. The same forward or backwards. And it's a true fact in general that the Eulerian number nk is the same as the Eulerian number of n minus k minus 1. Now, every good math talk should have at least one joke and one proof, and they should not be the same. So here we're going to attempt the proof. All right, so what's the proof? Well, we're going to do a bijection. So suppose I start with any permutation at all, and so again, right now I have 3 drops. What we do is we shift everything 1 over to the right, and so that last column becomes the first column. And after you do your shift, you now transpose. And so you end up with what's over here on the far right. Now if you look, this region, we know we started with k, so there's k rooks there. There's 1 rook that has to be in the top row, so that's k plus 1 rooks, meaning that there's n minus k minus 1 rooks left to go into that slot. And therefore, I can do this bijective relationship between the different types of counting. So now, with this in mind, we can talk about Pixies' identity, which says the following. X to the n is the summation over all k of the Eulerian number nk times x plus k choose n. Now, you might look at this and think of, okay, is this really something that should be true for all arbitrary x? And the answer is yes, if you think of this x plus k choose n as essentially sort of an x plus k following. So it's x plus k times x plus k minus 1, so forth and so on, until you get n terms divided by n factorial. Now, why might we care about this? Well, in algebraic combinatorics, they oftentimes say it's nice to have different ways to represent the same polynomial. And different polynomials have different strings. Here's a really clean example. Suppose I wanted to talk about sums. Now, sums of certain objects are much easier than sums of other objects. So, for instance, the sums of binomial coefficients are very easy. So imagine that you have your Pascal's triangle, if you filled it up as a grid. And now you start summing down a column, and you stop. You say, what's the value of all those numbers? You just go 1 over and 1 down. That's the value. So I can sum up binomial coefficients very, very easily. All right, well, how do we use that? Suppose I want to sum up j to the n. That's not so easy. But if we could translate j to the n to binomial coefficients, we make our life better. And that's what Pixies' identity does. It says, okay, I can replace this j to the n in terms of something involving binomial coefficients. There's finitely many terms, so I can rearrange the sums. And so I have a sum of a nested sum now. But this nested sum is exactly the kind of sum that we have here. And so I can replace it in terms of binomial coefficients. And so now I can sum up powers, j to the n. I can get a pretty nice clean expression. All right, so where are we going? Well, we're going to give, like I said, a nice proof of this. We're going to do it by juggling. So you were promised some demonstrations. So let's talk about juggling, and let's do some demonstrations. So we're going to start by talking about juggling diagrams. And there's a couple of different patterns that we're going to talk about. Most diagrams are, most juggling patterns nowadays are named by mathematicians, and we'll explain why in just a few minutes. These are a few patterns which have other names, so that if you go and talk to jugglers, they'll say, yes, we recognize these patterns. So the first pattern is the 3-ball cascade. So this is the one which, if you're going to learn how to juggle, this is one you start with. It's a very easy pattern, and it looks more or less like each ball is making a figure 8. Now, how do we represent it? Well, imagine that you were juggling and you turned, and then you just started walking. Well, if you do that, you can actually follow the balls through the air. And you'll see the balls are going up and down, up and down. So we're thinking of each one of these different colors here as a single ball, and we're following what's happening. Downstairs, we're looking at the beats. So at each beat, an action happens. A ball comes, you have to do something with it. You throw it again. The height of it tells us how far we need to throw the ball. Now, of course, I should point out that the motion of walking with the juggling is not very unusual. In fact, a lot of people, when they first learn to juggle, they actually start chasing the balls, and that gets into something known as juggling, which is a different sport. So, all right. So that's the 3-ball cascade, but that's not the only pattern. There's actually a lot of patterns. There's also something called the 3-ball shower, and that has a very different feel to it. And if you think about what was happening, you'll see that in this one, the ball from my right hand is going up very high, but the left hand is going very low. High, low, high, low, high, low, high, low. And you can see that. It's a high throw, then a low throw, then a high throw, then a low throw. And it keeps going on and on. Now the last pattern I want to talk about is the baby juggling pattern. And you hear that and of course you say, okay, baby juggling. I know what that means. So, not quite that, a little different. So the baby juggling pattern comes from this notion that a lot of old jugglers would say, look, I want to incorporate all sorts of things into my act, including my kids. So they would hold a baby in their one arm, they'd take the two balls, and they'd throw these two balls up very high. And then while those balls were in the air, they would switch the baby to the other arm. So that the baby was actually the third ball. And that's this ball that you see down here. Now, I don't actually use real children, but I will say that if you go online, there's a recording with Alan Knudsen doing this with a young toddler. He's a much better juggler than me, but I can attempt it with the balls. And so we need to have a ball for the baby. I'll use a baby ball. It's nice and small compared to the other ones. And let's see. It looks something like that. So you have two balls going up high. Whoop! Wasn't the baby, so. You have two balls going up high, and you always have one ball going down low. All right. So I mentioned that, of course, mathematicians get to name things nowadays because mathematicians, the way they really came into this was they said, hey, these are patterns. Let's find some ways to describe it. So there's something called siteswaps, which we'll get into later on. But this is how jugglers now talk about juggling. They use numbers. So this number here, 3, indicates that what you do is that each beat you throw a 3. So what does that mean? That the ball would land 1, 2, 3 beats in the future. And every beat lands 3 beats, every ball lands 3 beats in the future. Here, 5-1 says you throw 5 beats, then you throw 1 beat, then you throw 5 beats, and then you throw 1 beat. So you can keep track. Now 5-1 and 1-5 are the same pattern, they're just slightly shifted in time. For our purposes, we're going to count these as distinct. There's ways to correct for that overcounting later on. You can use Mobius inversion. This baby juggling pattern is a little bit more complicated, but again, it's 5 beats, then 2 beats, then 5, then 1, then 2, and then it repeats. So we want to count how many juggling patterns are, and we're going to do this in 2 different ways. So the first way we're going to count is do a little bit of card counting. And so how are we going to do this? Well, we're going to sort of say, well, what's happening at each beat? So what's going to happen is one card represents 1 beat. And we're going to say, well, what happened? Well, it's possible that you threw all the balls up so high that in that particular beat, there's nothing for you to catch. And so in that time, just everything is moving closer, nothing happens. But most of the time, the ball will come down. So if a ball comes down, you're going to throw it again. And what we want to ask is, okay, what's the relative order of the balls? In other words, how are they going to land? Because there are 3 balls with these sets of cards. And it could be that the ball that you threw was such a low throw, it's the next ball that you throw again. We saw that, for example, in that 5-1 pattern, where you had a 1, and then you would automatically throw that ball a second time. So it was a very low throw. Or it might be you throw it a little bit higher, so that one other ball will land in the meantime. Or maybe you throw it very high, so that both of the other balls will land before that ball lands again. Now the nice thing about these cards is it's very easy to take the cards and make a juggling pattern. And the way you do it is you think about, well, I have the diagram. So I just lay down a series of cards, any order I want. And I place my cards, and say I want to repeat every 4 times, so I place 4 cards, and then I just keep repeating those same 4 cards over and over and over again. And if I do that, what I get as a result is I get a juggling diagram. This is a juggling diagram just drawn in a very stylish way. And once I have a juggling diagram, I can figure out the pattern. So for instance, I can talk about the throws. If from here, I want to land in 1, 2, 3 beats. Here, 0, because there's no throw. So 0 represents no throw. Here it's 1, 2, 3, 4, and then 1, 2, 3, 4, 5. 3, 0, 4, 5. And that's the pattern. Now, if I was a better juggler, I would say I can demonstrate that for you. I'm not a better juggler. I'm an okay juggler. But fortunately, there is an app for that. So, you should always have someone to demonstrate your juggling. And if you go online, you can do all sorts of fun things, such as type in a pattern, 3, 0, 4, 5, and say, okay, what does that look like? And the answer is, That's what it would look like if you juggle it. So this makes it a lot easier. You know, one of the nice things about juggling nowadays is you don't have to wonder, is it actually going to work? See, in the old days when people were learning how to juggle, they didn't know. And so the question is, are you struggling because it's impossible? Or are you struggling because it's hard? There's a difference. There's a difference. Now, what do we have? If we place a series of cards, we get a juggling diagram. But the real question is, do we get all the diagrams once? In other words, is there a nice bijection? And the answer is yes. So the way you figure this out is you say there's a question. How many balls will land before the ball throwing lands again? Now it's a slightly different question than how many beats. So for instance, here if I look at this red ball, how many different balls will land before that ball lands again? Audience participation.
Blue and green.
All right, the blue and green ones will both land before landing again. And it's okay that the green one lands multiple times. I just want to ask how many different balls will land. So the answer is that there are 2, which means that when you choose that card, I need to have it so it goes up above 2 cards, or I should say the 2 balls existing. How about the next one? 1. Okay, the next one? 2. The next one? 0. But it's a throw, so we need to have the variation that has a throw. Okay, one more. 1. Now the reason I say one more is you might recognize this pattern. This is the baby juggling pattern. And we know it repeats every 5 times, so as soon as I have that, then I can just fill in the rest. It keeps going. So, what do we have? Well, the number of juggling patterns with less than B balls in period n, well that's the number of ways I can place B different types of cards in each of n slots. So n, because that's the period, that's how many times before I repeat, and B, because you have to remember the picture here. When I had 3 balls, there were 4 cards, because there was that extra card of no throw happening. So if there's less than B balls, then there's going to be B different cards available. But anyways, the point is that this is an easy count thing. This is a great count. You know, it's B to the n. B times B times B times B. All right, good, good. Halfway done. We've counted half of it. Well, what's the other half? Now we got to get into site swaps. And in particular, what are called minimal site swaps. So remember, a site swap, it's how you make the throws. So it's a series of numbers, and the series of numbers say, what kind of throws are you making? So we keep track of throws like T1, T2, up to Tn. Now there's a couple of facts, and these are not so bad. One of them is, how do I know if my series of throws is actually juggable? Because it could happen that my balls could collide. So a very simple way to demonstrate this is you have what's called 2-1. Now 2 is a very easy juggling pattern. To 2, if you're a juggler, it just means hold on to the ball. And 1 says throw the ball into the other hand. So if you have a 2-1, the problem was the hand was already full. It couldn't catch the ball. So not every single set of numbers forms a pattern. So you have to be careful. So what you check if I plus T sub I mod n are distinct. If they are, it can definitely be juggled. If they're not, you're definitely going to have balls hitting one another. The other fact is that the average of the throws is the number of balls that you need in the pattern. And if time allows at the end, we'll get into why this is true. So these are some facts about site swaps, but I want to talk about minimal site swaps. Minimal in the sense of the following, in that the only types of throws we allow are very sort of short throws. So between 0 and up to n minus 1. Now, the nice thing about minimal site swaps, well, there's a couple of nice things. First off, any site swap you have, I can get to a minimal site swap. And the way I get to a minimal site swap is I take things modulo n. And that's coming back to this first fact. Because if I do things mod n, it doesn't affect whether or not the first fact holds, whether things are still distinct. So I'm still safe. So if I could juggle before, I can still juggle after. The other nice thing about minimal site swaps is we can now think about how to represent them. And this is starting to look very familiar. We can have a board. The rows are the times that we throw the balls. The columns are the times that we catch the balls. And we say, all right, well, every time we make a throw, where there's going to have to be one thing in each row, and in every column we have to catch, so there's going to be one thing in each column, and so we get a rook placement. Now, what are the entries on this board? Well, the entries talk about what type of throw do you make. So as an example, if I throw at time 2 and I want to land at time 4, I'm going to go from 2 to 4. So that's 2 steps. If I want to throw at time 4 and land at time 2, well, I'm going to go 1, 2, 3 steps. So what's really happening here is we're actually just sort of changing our perspective of time. Instead of thinking of time as a line, we're just going to say, oh, it repeats every end, so we're just going to wrap it around. And we're keeping track of what happens. So now we can answer at least one easy question. We are interested in counting things. How many minimal site swaps are there?
As many entries in the board?
Well, there's n squared entries in the board, so there's more than that. Let me phrase it to you the way I might phrase it to undergraduates. Is the answer n, or is the answer n? This was not meant to be a trick question. Which one is it? N or n?
N!
The n is correct, yes, n factorial. Because what you get is you can think of it as like, I get to pick a rook in each column. There's n choices for the first one. I lose a choice for the second one, so now I'm down to n minus 1, n minus 2, and so forth and so on. It's the number of permutations. So for each permutation, you have a minimal pattern. And now we start thinking, hey, how do we get back to our Eulerian numbers? So what do we say? Well, Eulerian numbers, they're counting what's down below. So what could that count? Well, it turns out that the number of cells that you pick in your pattern is equal to the number of balls that you need. So that there's this nice connection going on. Now, why is that true? Well, that comes from the fact of that the average of the throws is equal to the number of balls. And you can check. Now, this pattern is a 3, 4, 2, 4, 2. So this is a pattern that can be juggled. In fact, that one's not too bad. I think it looks something along the lines of this. So this is the pattern 3, 4, 2, 4, 2, where you have things going up and down and back and forth. And if you take the average, well, you get 3 plus 4 plus 2 plus 4 plus 2. That turns out to be 15. Divided by 5 is 3. You'll see there are 3 that are below the diagonal. And it's always the case. So now we're going to count all site swaps. Remember, so far we've just counted the minimal ones. And the way we do it is you say, okay, now if I want to get all site swaps, I just have to bump all the throws up by multiples of n in all possible ways. So the goal is to say, let's sort of demonstrate. I have period 5. I want to say there's less than 8 balls, because these are my 2 parameters, n and b. And I want to show how I would end up with this pattern, 8, 4, 12, 4, 2. So the way we do it is we start with a minimal pattern. In fact, we're going to start with this one right here. And we want to bump up the entries. So step 1, pick a minimal pattern. Well, we use Eulerian numbers, and here I'm using the fact that I have symmetry available to me. You'll see why in just a second. All right, the second step is to say, okay, I need to bump up my entries. So I'm going to do what's called a bars and stars argument. So I have n throws. I'm going to have n plus 1 entries. Now, why n plus 1? Because I want to be able to bump up any entry, and I want to have sort of a, oh, I don't want to use all the balls. So this is sort of an excess ball. Says, I'm not going to use that ball. So I can distribute my remaining balls into these different bins. If I do it here, so this is n equals 5, 3 plus 5 gives me the 8. Leave that 4 alone, bump 2 up twice, that gets me to 12, 4 and 2, and then there's 1 ball we're not going to use. So for bars and stars, you can count that using binomial coefficients. Now what do we need to do? Well, this assumes that we fix the number of balls that are in our minimal pattern, so we sum over all possible ways to get the number of balls in our minimal pattern. And now we say, hey, to simplify our sum, replace this expression, n minus l minus 1, with just k. And if you do that, you get a very nice, simple form. So, what have we done? Well, we've counted the number of juggling patterns of period n with strictly less than b balls in 2 different ways. We did it by saying how many different ways are there to count by cards, and the cards are keeping track of your relative ordering. We also said, well, let's count by rook placements in bars and stars configurations, and this is generating the site swap. And because we are counting the same thing in 2 different ways, these 2 things have to be equal to each other. and therefore this establishes Pixies' identity. You might be worried in that we only prove this for whole numbers, but because Pixies' identity is a polynomial identity, if you prove it for enough numbers, then you prove it for all values. So the other thing you might say, if you're new to the game of counting, is to say, this is such a beautiful count. Why would you ever do things this way? Well, the answer is that there are cases, even in juggling, where this is not very useful. You have to actually dig into this particular one. As an example, I want to talk to you about the odd juggler. You might be thinking, I've met jugglers. They're all odd. But when I talk about the odd juggler, what I mean, it's a juggler who can only make odd throws. Now, in terms of actual juggling, that means that odd throws are the kind that go between your two hands. So you can throw from your left to your right, or your right to your left. An even throw is a throw that goes up and down and stays in the same hand. So the odd juggler always wants to throw balls that cross. So the question is, how many patterns are there? Suppose you have B balls in period n. Well, some of these counts are pretty easy. As an example, if n is odd and B is even, it can't be done. And why is that? Well, remember that if you look at the average is the number of balls. And if you have an odd number of odd values, you can't have the average be an even number. So that just can't happen. If n is odd and B is odd, it turns out that because of modular conditions, you can actually say, all right, I can get it down to saying that all the patterns which follow the odd juggler, I can relate back to patterns of B minus 1 over 2 balls with no restrictions at all. So you can count them. What about n even? Well, the answer is this formula. So it's a sum, it's a double sum now, sum over all ij, the auxiliary number n over 2i, auxiliary number n over 2j, and a binomial coefficient. It's actually surprisingly similar to the total number of counts for just without any restriction. Now you might say, is there a simpler form to write this in? And this is the simpler form. So this is as nice as an answer as there exists. Now how does this one work? Well, because n is even, we can actually rule out a lot of placements in terms of our minimal patterns. Because I can't start with an even number and add an even number and get an odd number. That automatically knocks out half the board. Then the rest of the board says, hey, you can split them into two different subboards, a yellow board and a red board, and they're completely independent from each other. So that's where you get these two different auxiliary numbers showing up. You pick something on the red board, you pick something on the yellow board, and you place everything else. And that gives you your final count. So I've been doing math of juggling now for quite a while, and I want to talk a little bit about some of the things I've done. These are definitely not all the things that I've done. I've worked with, to the best of my knowledge, there are two mathematicians who have written more papers about math of juggling than balls that they can juggle. And I'm one of them, because right now I'm at 4 balls. Now I'm working my way up to 5 someday. The other person is my advisor, Fan Chung. She's at 2 balls that she can juggle. And so someday, maybe 3. Well, maybe not. So I like to work with younger people. So these are a group of high school students who came from South Korea to work with me. And we were able to do the following. This is something that came out, was published earlier this year. We were actually able to count multiplex juggling patterns. Now you hear the word multiplex and you're like, ooh, juggling patterns in movies. But actually multiplex just means many balls. Many balls coming at one time. And before we were able to attack the problem, it was actually something that couldn't be counted before. But we were able to find out that by using cards in the right way, introducing a new type of cards, we were able to do it. Now here, there are 4 young people in the front. You might recognize Scarlett, who's was a graduate student, Esther, Jason, and I feel bad, Jeffrey. The other people, Eric Demain, he's a mathematician at MIT. He actually created a font based on juggling. This is me. This was taken several beards ago, so I had less gray in my beard at the time. This is Colin Wright, who invented siteswap. You can see he's not that old. He's still pretty young. Ron Graham and Glenn Hurlburt, who's in the picture for some reason. He's a nice guy. I like Glenn. And so with the REU group, together with Chris Cox, who got his master's degree here, we did a couple of things. We came up with a nice generalization of Eulerian numbers, which says, okay, instead of thinking about them as rook placements, what if you have 2 rooks in each row and 2 rooks in each column? What do you do then? How do you count them? And we were able to figure that out for a small case. And the other thing we did is count prime juggling for a non-trivial case. So I want to talk about this last result because I think it's a very nice result. And it's something that sounds easy, but it's not quite very easy. So before we can get to that, we have to go into yet another way to describe juggling. So there's something called juggling states. And the idea is pretty simple. The idea is, you're juggling, and after a while you're getting bored. It's like, ah, so you stop. Now, what happens is you listen, and you hear a tut, tut, tut. That means just all the balls just landed in a row, each on the next beat. But I could have stopped at a different point, and depending on the pattern, if I stop at a different point, I might hear a thud, thud, and then a very dramatic 2-beat pause before my last thud. Again, I could stop at a different point, and then I'd get a different pattern that I would hear. Or keep moving along until eventually I get far enough along. Now, if of course you recognize this pattern, perhaps, again, back to the baby juggling pattern, you'll see we repeat. So the states talk to us about when are the balls coming into land? Or if you were, like I said, to stop, when would they hit the ground? So the nice thing about states is that they perfectly describe your juggling pattern. In other words, if I know my juggling pattern, I can figure out the states I'm in, and vice versa, if I know all the states, I can figure out what juggling pattern I'm in. So how does that work? Well, just think about what's happening. Let's suppose here are the 5 states we had before, and again, because it's periodic, it's going to go around. In a juggling pattern, what will happen is I can only affect the ball that's in my hand. I can't use telekinesis to change anything about the balls that aren't in my hand yet. So these 2 balls here are going to move closer. So the last 2 ones here shift down, become the first 2 ones. This ball, that's in my hand, I need to throw it. In this case, it has to end up there. So I can see that this transition has to correspond to throwing this ball 5. And you can go through and each one of these. And if you do this, you'll see that, let's see, this is a 5, this is a 1, this is a 5, this is a 1, oh, no, anyways, it's 5, 2, 5, 1, 2. I started at the wrong place, I apologize. Once you have the idea of a state, you can talk about a state graph. Now what's a state graph? Well, you look at all the states. Now, I say it's an infinite graph because you can imagine that you have a really good arm. And you can throw that ball really high. And if you throw that ball really high, you can get lots and lots of zeros. And so we'd like to draw this part of the state graph because if you're a 3-ball juggler, most of the tricks that you learn are in this part of the graph. And so what can you do is once you have all the states, you put in all the transitions, and now you can sort of explore what's happening with juggling by looking at this state graph. So we can point out some of the patterns that we've been doing. They're all here, all the ones that we've talked about. So this pattern here, this 3, that corresponds to the 3-ball cascade. The 3-ball shower, the 5-1, 5-1, that's going back and forth. So that's that pattern there. And now you can start to explore. You can say, okay, are there any patterns we haven't learned yet? Well, if you go here, 4, 4, 1. That's a very important pattern in the history of mathematics. So that pattern looks something like this. So 4, 4, 1, 4, 4. Ah! So why is this important in the history of mathematics? Well, because the mathematicians went to the juggling conventions and they were talking to the mathematicians and saying, hey, we got this cool thing, it's called siteswap, you're going to love it. And of course the jugglers were like, yeah. And then the mathematicians pulled out this trick. And I'll tell you, it blew the jugglers' minds. They're like, we've been juggling for thousands of years, and we've never seen that. How'd you find that? And the answer, of course, is math. Because math gives us a systematic way to explore and figure out what's going on. And without that systematic ability, lots of patterns would be lost. All right, so what's the point here? Well, now the point is you can start to explore patterns. And so every closed walk is a juggling pattern. In other words, you start and stop at the same point. And you can also start to think about transitions between patterns. So by that I mean, you might say, all right, suppose I want to transition from the 3-ball cascade into the 3-ball shower. Well, if you do that, you'll see that you have to sort of like have a little hiccup in your pattern because they're not right next to each other. So there's sort of like an off beat. On the other hand, from the 3-ball cascade into the pattern 4-4-1, back into the 3-ball cascade, you can do that without missing a beat because they're right next to each other. And so it's pretty smooth, assuming that you don't have a sudden gust of gravity. All right, so what was the problem that we wanted to look at? Well, the problem is, what if you want to count prime juggling patterns, and these are closed cycles? Now, the difference between a cycle and a walk is, are you allowed to repeat your states? So in walks, you're allowed to repeat. But in cycles, you're not. So the pattern 4-4-1, that's a prime pattern because it's a cycle. The pattern 5-2-5-1-2 repeats this 1-1-0-1. In fact, you can see it over here. This is the 5-2-5-1-2. It's repeated. So it's not prime. The idea of prime is the idea of being able to break it down. So you can think of the 5-2-5-1-2 as a combination of two smaller patterns that happen to overlap. So the prime patterns are the ones that you can't break down any further. So it's been sort of like the holy grail in math of juggling. How many prime patterns are there? And the best result before ours for prime patterns, in terms of prime patterns, was the following. If you have one ball and period n, there is one prime pattern. And that was the best result that was known. That was not a hard result to prove. Now, Fan Chung and Ron Graham looked at a slightly related problem. They said, okay, look, a closed closed cycle says you never have a repeated state. What if we insist there's one state that never repeats? They call those primitive. And they counted those. It took a little bit of work. It turned out you can do it by taking permanents of particular matrices. Okay, so what's the result? Well, we got to 2-ball patterns. And here we go. So this is a result from working with the undergraduate students. So the number of prime 2-ball juggling patterns of length n is about 1.329 ... This is a very specific constant. I'll give you an explicit way to generate this constant times 2 to the n. So I want to go through and sort of sketch the proof here. So this is the technical part, so you really came to a math talk. It'll help you fall asleep as we go near the end. So how do we do this? Well, we go back to cards. We say, remember that we have this way to use cards. And so if I have 2-ball patterns, there's just 3 types of cards. There's one type of card that says the balls were up pretty high, nothing happened. Another type of card that says you were juggling, and then what happens is you cross over. So you throw the ball so that you're ending up crossing over. And then the other one says it's a pretty shallow throw, so you're just moving a little bit closer. All right, so those are our 3 types of patterns. And therefore, we can say, well, what's true, every 2-ball pattern is going to be some combination of these 3. But we always have to make sure we use at least one x. If we use less than one x, it's a 0-ball or a 1-ball pattern. So that's what we're going to count. Now, how do we make sure everything is prime? Well, all I have to check are a certain type of state. So namely a state where I have a 1, a bunch of zeros, and a 1. So in other words, I just always move things until I'm ready to throw. And I just check, do I ever repeat a state of that form? If I don't, I'm prime. If I do, I'm not prime. So from here, we say, all right, what do we do? Well, we want to do the following. We want to say, if I have a state and a state, I always want to measure the gap in between. So I want to figure out, how do I measure that? So if I ever have an x, that's a ball that crosses over. So anything that's after an x is essentially the further up ball. So we're going to mark everything that follows after an x. We're going to put a little anchor on top of that to say, okay, that's the second ball. And now what I do is I can measure how far am I away from a second ball. So we go through every number and we say, okay, how far are you from that second ball? And for instance, here, that second ball would be 1, 2, 3, 4. Next one would be 1, 2, 3. Here it's 2. Here it would be 5, because remember, we wrap around 1, 2, 3, 4, 5, and then 1. I'm prime if and only if all those numbers we've produced are distinct. All right. So now we're getting close. So we're going to group these distances to each anchor. So for this anchor, there's 2 distances, 4 and 3. For this anchor, there's just the 2. For this last anchor, there's 5 and 1. So now I want to sort of get a count of this type of object. So in particular, what we're going to do is we're going to create a bijection between our prime 2-ball patterns of period n and the collections of disjoint sets where the sum of the largest elements is n. So the way we're going to do this is we're going to say, okay, suppose I know what the largest elements are. So let's say I knew them. They were 11, 7, and 2. So those are my largest elements. Now I say I have to populate the rest of the sets. And so I say, well, that leaves me with numbers 1, 3, 4, 5, 6, 8, 9, and 10 to play with. And so to count how many ways I can do it is I can say, well, where can 1 go? It can be associated with any of 11, 7, or 2, or I don't have to include 1 at all, which is why I say there's 4 options for 1. But if I go to a later number, say like 5, I can associate it with the 11 or the 7, but I can't associate with the 2. There's not enough space. But of course, again, I don't have to include it at all. So once I know the largest numbers, I can say, well, the rest of the way to populate the sets is the product. 4 times 3 times 3 times 3 times 3 times 2 times 2 times 2. So we're going to do a quick count. We fix a partition of n. Right now it's ordered. And then we say that the number of sets, given this information, well, I count, and these numbers here are coming from these numbers downstairs. And if you clean it up, you get to a certain expression. All right, that's not so bad. There's a couple of things you have to be careful of. One thing is, we have to remember that there's also, we don't care the order that the sets came in, because right now there's this natural ordering of our partition. So if we have our ordering of our partition, we can reorder them in any way we want. There's t minus 1 factorial different orderings. And then the other thing, of course, is we can say, well, look, you can have lots of different parts. And so we get the following intermediate result. And this is an exact count. So the number of 2 juggling patterns with period n is the sum over all t, sum over all partitions of n. 1 over t times t plus 1 times this product. And if you're wondering where the t times t plus 1 comes from, it's t minus 1 factorial over t plus 1 factorial. Now you might think this is not what we started with. We said it was something 2 to the n. Well, now comes the analysis. So if you play around with it, suppose you say, let's call these ct of n equal to this expression. You can then group this according to the size of the smallest part. So you group by the size of the smallest part and you get a recurrence. And now with a bit of work, and this is truly a bit of work, you can conclude the following. That ct of n is approximately 1/2 times this product of I minus 1 over 2 to the I minus 1, and then times the 2 to the n on the end. Now, this approximation is actually really good in the following sense. The error grows at order root 3 to the n. So it really is growing at 2 to the n. That's not just a really bad approximation. And so we put it all together, and we can say that the number of 2 juggling patterns, well, we just sum these terms, these ct of n, and therefore we get that it's this 1/2 times this crazy looking expression times 2 to the n. And this number, that's where that 1.329 was coming from. The nice thing about this number is that it converges very, very quickly. The bad thing is it's not a very good number to work with. It's a very, very strange number. I will say that when the data was first coming out, because we were computing the data, we were like, okay, it's like 1, it's like 1.2, and it's like 1.3, it's like, oh, 1.32, and it's like, I was getting excited, and I was like, oh, it's going to be 1.333, it's going to be 4/3, it's going to be so beautiful. It turned out not to be that number, but that's okay. It was a good number. And I should say that we have checked this. So we have, for example, up to n equals 100. And we said, okay, how does this estimate compare to the actual? And it was within 0.00001% of the actual. So it's very close. Well, so that's the result. That's what some of the results that I've been able to work with on students over the years. And so I'll say that math is about patterns. And there are patterns all around us, and juggling is just one example. Of course, there are many more. You know, mathematicians came in, we made juggling better. It's not the only area that happened. You know, you look at origami, mathematicians came in, origami got better. You know, just about every field. Once the mathematicians come in, things get better. And I think this is a good place to stop, so thank you for coming.
Steve, I have a question.
Sure.
All the patterns you talked about are deterministic patterns.
Yes, they are.
If they were random patterns, there should be some laws of large numbers.
Well, I mean, so if you're doing randomness,
Something like that?
the closest thing you can get to randomness, so there's Greg Warrington, who's at Vermont, wrote a paper called The Random Juggler.
Okay.
And so his paper was, suppose I'm in the state graph here,
Yeah.
and I'm juggling, a ball comes in, I have to juggle. What that means? Well, that means I have to pick an edge to go off of. And so maybe I go this way. Okay, now I have to pick another edge. So that you can think about the random juggler as somebody who's moving around in this state graph. And so the question became, well, can you say anything interesting about, where do you spend your time? And the answer was, you spend a lot of time in this state, the 1-1-1 state. And it turns out that, I don't remember the exact forms, but you get Stirling numbers showing up in terms of where you land.
What number?
Stirling numbers? I think Stirling numbers are the second kind, if I recall. So it is possible to do random juggling. In fact, a lot of counting you can tie in some way into juggling. And
that number that you wrote down.
Sure.
Is an infinite series.
Right.
And you prove that it converges.
Well, yeah, I mean, it definitely converges, because if you just look at the growth rate, you have these massive powers downstairs of 2 to the I, and upstairs it's fairly small, and these are like a bunch of products of 2 to the I. So yeah, I mean, it doesn't just converge. After 3 or 4 terms, you got the first 100 digits. So it's rapidly converging. But as far as that, it's an amazing number, because this is not the number you would think of.
Right.
And it sounds like such a simple problem. It's like 2 balls. How hard could it be to count 2-ball patterns? And the answer is it's incredibly hard. And this is not the only time when just counting simple patterns is hard. So there's a problem. There's this Japanese juggler who has this big plexiglass sphere. Then what he does is a small hole, so he can reach in and he can take a ball and he'll start at the North Pole and he'll just roll it, and it'll roll around the inside of the sphere, and then he can catch it. But then he can roll it on different great circles. Now, of course, this is really hard to travel with. If you're gonna, that's definitely a carry-on type item. But the question becomes, okay, what's the math of juggling there? Well, we can talk about the math of juggling on a sphere, and when we talk about collisions, balls colliding, the only kind of ball collisions we worry about are when balls collide in your hand. But on the sphere, well, the hand is the North Pole, but the great circles also will converge at the South Pole. So now there's an extra collision point. And there's just nobody knows how to count that. I mean, nobody. And again, I have the best result, and that's a kind of cheating, and I can count 2-ball patterns. But even then, it's 2-ball patterns where you add a restriction. And so, there's a lot that's hard to do. On a side note, there will be a book coming out, Juggling Counts, hopefully early 2021. So, and some of you will not be here, but if some of you are still around in that time, I hope to do a class for math of juggling. Again, that'll be fun.
Has there been much connection between the math juggling literature and the Latin square literature? For example, siteswaps related to complete mappings?
There has been some connections. The person who I've corresponded with is Ian Wanless, I think I'm pronouncing his name correctly, who's down in Australia. So there are some connections, and certainly there's sort of, there are some interesting problems which are not too far off from these types of things. Like one of the problems which it sounds really easy, is the following question. Suppose you want to say, there's this famous result, and now I just want to make sure I get the right, oh gosh, I'm going to forget names, but there's this famous result that says if you have a set of numbers whose average is a whole number, then you can always rearrange it, and that can be juggled.
So you can always rearrange it, the system.
Yeah, so one of the things I said before was if you have a juggling pattern, the average of the numbers is the number of balls, which means the average is a whole number. But there's another result that says the opposite is almost true, which says if the average is a whole number, then you can find some way to rearrange the numbers, and then that will be juggleable. So that's a result, and that's not really a math result. It's a juggling result. That's really a algebra result that's been applied. But then there's the question that says, okay, which pattern or which set of numbers is highly reorderable? In other words, you can reorder them and you can get as many as possible. And that's turns out to be a really challenging question. We don't actually have an answer to that. We have a guess, but we don't know. But you start with a guess, and then you get a little bit better. So, yeah, there's still a lot to be done. Hopefully there's still enough math for a second edition of the book in a couple of years.
More questions? Let's send Steve again.